All right, this is for Chemistry 1151. We're going to finish out Chapter 6 with Section 6.5 and 6.6. So in this last section, we're going to talk about equilibrium. And so this is what I was telling a lot of you in class, that the definition that you may have for physical versus chemical change is that physical changes are reversible and chemical changes are not reversible. Actually, chemical changes sometimes are reversible. And so we're going to look at reversible chemical reactions today. A reversible reaction can go in either direction. It can go to the right and it can go to the left. And so we use these little back and forth arrows, and you can write a full arrow, but we usually don't do that because it's kind of hard to fit in like a reasonable amount of space. It also takes longer to draw if we do like an arrow like this and an arrow like that. And so we just do these little half arrows, one going right and one going left. It takes a lot less time to draw and takes less space to make it a little bit neater. So that's how we show reactions go both ways. And then we call it a system in equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. I highly recommend that you remember this about equilibrium, because a lot of people get it confused with the concentration of reactants and products have to be the same. And so the thing that's equal at equilibrium is the rate forward and the rate reverse are equal. The products and the reactants do not have to be equal. They can be, but that's not what's equal at equilibrium. And so imagine that if one of these and one of these turned over here, then one of these and one of these would go back, right? And so that would be equilibrium. Like if one person, if there's a packed, you're trying to get into like this brand new restaurant or something like that, right? And everything's packed. If a table leaves, another group of people come in, right? The same number of people that leave, two people leave, two people in. Four people leave, four people in. That's equilibrium. It's not that the people inside and the people outside are the same, because you could be at a restaurant where there are only 8 people inside and there are 20 people outside waiting for a table, right? The number of people inside and outside are not the same, but if 4 people leave the restaurant, 4 people will go into the restaurant, if that makes sense. The rate of people leaving and the rate of people coming in is the same. What happens is the net change between the amounts of reactants and products don't change. So we talk about my example here of 20 people outside a restaurant and 8 people in a restaurant. If two people go in and then 2 people go out, there will still be 20 people outside and 8 people inside the restaurant, right? So the amount of reactant and product, the amount of people on either side, have not changed. And so this is going to be when the reactants and products no longer are changing their amounts, but the reaction is still going back and forth. We just don't see it actually change when we're measuring the amount of reactants and products. When you're at equilibrium, so when you get to this state where the amount going in, the amount produced, and the amount going in reverse are the same, and the amounts of reactants and products are no longer changing, then we can come up with this constant, equilibrium constant K. So K is a capital K. It's an equilibrium constant. That's just the letter that it is. And we use brackets to symbolize concentration. So concentration is the amount of stuff that you have in the amount of space. You've done concentration stuff before. If I add a lot of salt to water, it'll be really concentrated. If I have, you've ever had really concentrated coffee, what you can do is dilute it by adding more water. Or if you've had too dilute coffee, you're like, oh, I wish this was more concentrated. And so you kind of know this term. It's basically how much stuff in the liquid, in the mixture. So it's how many moles per liter. And so we'll use this concentration, moles per liter, and we also write it as M, big M. So you may see me write big M for that. Don't worry about doing the math and stuff for molarity. We were not going to really dig too much into that just yet. Basically, though, the equilibrium constant is a way for us to tell products versus reactants at equilibrium. So what does that equilibrium look like? Is it like our restaurant example, 8 people inside, 20 people outside? Or is it the opposite? Maybe there's 8 people outside and 20 people inside. What does it look like for reactants and products? Are there more products at equilibrium? Are there more reactants at equilibrium? Are they equal? And the K value is going to give us that information. And so it is products on the top, reactants in the bottom, and these brackets again mean the concentration and molarity. So notice what we're doing here. We have the product raised to the coefficient. So we have to make sure we're balancing our equation. Then we have the other product raised to its coefficient. Then we have the reactant on the left side raised to its coefficient. And then we have the second reactant raised to its coefficient. And now we always call reactants the thing on the left side. Even if it's a reversible reaction, we're still going to call them reactants because we have to have names that are the same. We can't switch it if we're going forward or reverse. We have to just say, okay, reactants are always going to be left side and products are always going to be right side, no matter if we're going in a reversible reaction or not. This is going to be really simple for y'all. You do not have to think about this really a lot in depth. You're just literally going to put the coefficient, raise the substance up to its coefficient. So we'll look at an example. So N2O2, these are our reactants. And so they're going to go on the bottom. And their coefficients are 1s. So we raise it to the 1. So I can say 1, 1, and you don't have to write 1s right when you're doing that, but you can raise it to the 1. You can see how I've done that. The products go on top. What's the coefficient? 2. So we just raise to our coefficients and put the substances in the brackets to indicate concentration, and that's it. And you will just be asked in a multiple choice question like, hey, what's the equilibrium constant for this thing? All you got to know is take the coefficient, which is the number that comes in front of it, and it goes to the power of that substance. Products on top, reactants on the bottom. It's all about what you're making compared to what you started with. When K is greater than 1, that means think about fractions. If we have like 3/2, that would be greater than 1, right? So products are more than reactants. So that means that however our products, whatever our products are, there's more of that at equilibrium. If your K is less than 1, think about 1/3, right? So it'll be a fraction less than 1. If your bottom number is bigger, then your reactants are going to be in higher amounts. If the products are in higher amounts, we'll say things like the equilibrium lies to the right. I mean, it's kind of shifted to the right, meaning it kind of is leaning toward the right. It's making more products to the right than it is reactants to the left. And then we can also say that it favors the products, meaning that the products must be maybe a little bit more stable, because why else would we make more of those at equilibrium? And then if reactants are greater, the K would be smaller, less than 1. It'd be a fraction, right? Because if you have a number on the bottom that's bigger, it's going to make you make yourself have a fraction less than 1. That means the equilibrium kind of lies to the left. It's a little shifted towards the left and favors the reactants, meaning the reactants are probably a little more stable than the products there at equilibrium. It still is going back and forth, but one of them is going to be more than the others. Can they be equal? Absolutely, they can be equal. But if they are equal, then K would just be equal to 1. So if K is around 1, and around 1 we say like 10 to the negative 2 to 10 to the positive 2, so like 10 to the 1, 10 to the negative 1, 10 to the negative 2, 10 to the positive 2. As far as the range of magnitude here, those would probably be in about similar amounts. Not exactly the same, but about similar. Don't worry about these tiny little details like this. You're only going to see examples where K is really big or really small. Just remember that when you're dealing with exponents, the negative exponent equals small number. Remember with like scientific notation. So go all the way back to Unit 1 if you need a review on this. A positive exponent means a bigger number. Bigger number, I mean, greater than 1. So greater than 1 and less than 1. Bigger versus smaller. So if you have a reaction, let's look at the K. 10 to the 82, is that a big number or a small number? That's a really big number because it's a positive exponent, and it's a big positive exponent. If I said, would you like to get a check of that much money? You would say absolutely yes, because that is, I don't even know if that much money exists in the whole world, right? That's a huge number. Think about 10 to the 23, right? How big that is. How many times would you have to move that decimal to go 82 times? That's a huge number, right? So the equilibrium lies very strongly to the right. So if you put hydrogen and oxygen together, you are pretty much going all the way to water. You're not going to have a lot of going back to hydrogen and oxygen. And that's true. We don't really see water being broken down into hydrogen and oxygen unless you supply it with lots of electricity to break it apart. And so you can also see if you had a really small number, right, like a negative 82, that would be a really small number, so it would be in the reverse. So here's a little table for you, equilibrium values of K, what it means, what products or reactants are favored. And then how would we calculate the equilibrium constant? And so we would write our equilibrium constant, and then you would just plug your numbers in. And so let's take a look at how we would do this. So first we would write it. We have our products over our reactants. Everybody raised to their coefficient. So raised to their coefficients here. And then we have this formula that we've made. You'll take the numbers you're given and we plug them into the formula. And we just solve it. It doesn't have to be that complicated. The unit for K is not molarity. Actually, this is a false statement. It's not that. The unit is always omitted. Let's just kind of cross out all of that, actually. No unit for K. Because usually they're molarities and they cancel each other out. But you don't need to worry about the units for K. You'll see us just do Ks with no units. And the last little topic for chapter 6 is a fun one. This is Le Chatelier's principle. It says that if you have a chemical in equilibrium and you mess with it, let's say you add some reactant, you take away some products, you change the temperature, you change the pressure, it's going to stress the system, and the system is going to move in a way to alleviate that stress. So if we're at equilibrium, we want to go back to that equilibrium state, because the equilibrium state is low energy state. So if you add more reactant, you're going to make products from it. So we're going to shift toward the product if we have more reactant. Think about if you're a bakery, okay? If I come and drop off a bunch of ingredients, well, you can make more cookies. And so if we add reactant, it's going to drive the reaction toward the product. The amount of products would increase, and the amount of the other ingredients. If I just dropped off flour, your other ingredient amounts would go down because you'd be using the flour and that I gave you, and then you'd be using all your sugar, vanilla, other stuff as well. And so if you add a reactant, shift away from the reactant toward the product. So I'll give you a little a thing in class, but if you add something, you're going to shift away from the thing that you added. So add away. So if I increase CO2, so imagine we have a magical bakery, and if all of a sudden I were to just drop off a bunch of cookies, and you go, oh, I can't sell these cookies, but I can turn them back into sugar and flour and whatever, then you would want to, because you can store them that way. So if I add a whole bunch of products, we're going to shift away from the product toward the reactant. So again, we're thinking about add something, shift away from the thing we just added. So if we add reactant, we shift away from the reactant. If we add products, we shift away from the products. If we shift away from the products, we add the reactant, or shifting away from the product, that means that these are going to increase because we're moving toward the left. We're going to make more O2, we're going to make more CO, and we're going to use up that extra CO2 that was given. What about if you remove a product? So let's say we remove some of the bakery goods. I go in and I buy all of your cookies. So if I buy all the cookies, now what are you going to do? You got to make more cookies. And so we're going to shift it toward the product. So remove, replenish. You can think of these alliterations to help you remove, replenish. So if you remove something, you got to go make more of that thing. So you can think about what way you're going to shift based on what you're adding or removing. For temperature, just treat heat as a reactant or a product. And earlier, or in the last video, we talked about how heat was a reactant if it's endothermic, and heat was a product with exothermic. So if I give you this reaction and I give you this information, delta H, that's a positive number, that's endothermic. So we can treat heat like a reactant. So if we add a reactant, we shift away. Add, shift, away. Add, away. Endothermic reactions absorb heat, and so if you give it heat, it's going to keep going toward the product. If you increase temperature, but it's an exothermic reaction, exothermic because it's negative here, then we would add a product. So we can think about our heat as being a product. If we add product, it's going to shift away toward the reactant. So again, add, shift, away. Add, away. And then alternatively, if we were to remove heat from an exothermic reaction, it would shift right. So remove, replenish. Just think of heat, figure out where it is. Is it a reactant, endothermic? Is it a product, exothermic? And then last little thing, pressure increases. If you increase the pressure, it's going to shift in a way to decrease the pressure because we don't want to have too high of pressure. So but what we're going to do is we're going to look at moles of gas, specifically moles of gas, because changing moles of liquid and solids don't actually do anything to help with pressure. Gas is the only one that's really compressible that we can do this with. And so we see 4 moles of gas on the left side and 2 moles. If I increase pressure, it's going to shift to more moles. Think about more pressure, you need fewer moles because we don't want to have as high pressure. Like more people in a pressure situation makes a situation worse. Let's have fewer people in a high pressure situation, right? I like to think about this as pressures increasing, and think about like squeezing a balloon. That means that volume is decreasing. Think about squeezing a balloon, right? You're going to try to increase the pressure of that balloon. You would decrease the volume, squeeze it, squeeze it, squeeze it. So if we have less space, we need to go to less moles of gas. I know that the word is fewer. That's the correct grammar, but I'm trying to get you here with this. Less space, less moles of gas. And less space means, think about a balloon. Squeezing the balloon, less space, that's also high pressure. So same thing. Pressure decreases, let's say that now we have more space. So pressure decreases would be like more volume, more space. Well, now we need to make more moles of gas so that we can increase our pressure again, get our pressure back up. So if you were to expand that balloon, well, we would have to put more moles of gas into the balloon to keep it the same pressure so that it doesn't deflate. Because you could pull the balloon apart, but it's not going to stay until you add more moles of gas into that balloon. So we think about it as more space, more moles of gas. You also think about it like a party. If you know you're going to have more space for a party, you can invite more guests. If you know you're going to have less space for a party, you might have to invite fewer guests. And again, this is always going to be moles of gas, so make sure you're not counting moles of solids or liquids or aqueous solutions. And then here's a nice little summary for you. If you just remember this page from almost everything in this video, then you'll be good to go. As far as the Le Chatelier's principle stuff, you still have to do the calculations for K, but those are pretty simple. Don't let them freak you out too much because they might have exponents in them or scientific notation. Just remember positive exponents, big numbers, negative exponents, small numbers, and then just write down products over reactants every time you think about K, so that you have it in front of you, you can visualize it. And then for these equilibrium changes, these Le Chatelier's principle changes, just write it down and move your arrows and think about that kind of stuff. I remember add away, remember more space, more moles, less space, less moles, and that'll really help you move along in this content. All right, we'll see you later.